Hello everyone and welcome to this lecture on noise. The outline for today's lecture is the following. First we are going to talk about basic noise concepts, then we're going to talk about noise in transistors, in CMOS transistors. Then we're going to talk about the noise performance in basic amplifying stages that we have already studied before. Then we're going to move towards noise in balanced stages, mainly differential pairs. Then we're going to talk a little bit about noise of antiparallel stages. Afterwards, we're going to study some simple tools for noise calculations. Then we're going to move towards the noise in the basic feedback configurations that we have studied previous lecture, and then we're going to run a big example on noise optimization. First, to understand the impact of noise in electronic circuits, probably the easiest example is to touch how the signal, an input signal is amplified in an amplifying chain. So typically we have a cascaded amplifier chain that takes a very weak signal and then amplifies. And the signal itself might come with some noise, but most important, the electronic circuits inside the amplifiers also introduce some noise. And here we have, for instance, we have our first amplifier that is going to add some noise, and it is going to be amplified at the same time as it amplifies the signal. This noise and signal appear amplified at the output of the first stage, and then the second amplifier amplified also the signal, the noise of the first amplifier, and then add also some noise, the green one that we see here. The last amplifier amplifies further the signal and then amplifies the noise of the previous stages, and it adds also some amount of noise that is internal to its circuit. So from this picture we can conclude that the noise of the first stage is amplified by all the amplifier chains and basically dominates the noise that it is added to the input signal. Another conclusion is that the amplitude of the signal it is largest at the output of the last stage, and that is something that we are going to touch in the next lecture, because when we talk about noise, it is actually the first stage, the one that normally dominates the noise performance, whereas for linearity it is the last stage. So the first one will be noise performance and the last one normally will be linearity. Okay, so today we're going to talk pretty much how to design and optimize the first stage in an amplifier. Okay, so we have studied a little bit about the Shannon theorem, and we have seen that the signal to noise ratio degrades the capacity of the channel in a logarithmic fashion. So one important aspect here is that the signal to noise ratio is already limited at the input of our amplifier chain. And it is because the signal source is normally comes normally in company with other noise sources that can be coming from different mechanisms. In electronics, typically sources have a resistive component and then it produces thermal noise, but there might be other noise sources as well. And well, we have that our signal comes already with some noise. It means that there is already a signal to noise ratio at the input of our electronics. Our design goal will be to keep the noise that we add from our circuits at acceptable levels. But what is this acceptable? In practice, this will depend on the application. The signal quality should remain at a specific signal to noise ratio. So so that it can be, for instance, demodulated. It can be the analog to digital converter that we place. It has a minimum quantization noise, and we should not make the noise of our system larger than this quantization noise, otherwise it will be unacceptable. So it will depend on these characteristics at system level, how much noise degradation can be acceptable after we implement our circuits and connect this to an input source. Noise is a random process, and typically we deal with it as a power, and it can be in voltage, RMS square of it can be current, RMS square, and mathematically we deal with it in can be done in time domain, but we prefer to do that many times in a frequency domain, and what we will want typically to have is the noise spectral density. And then when we have this noise spectral density, that it is noise spectral power density, it can be expressed as voltage squared over hertz or ampere squared over hertz. We integrate it in the band of interest. So our signal will be typically limited by a particular band, and then we will filter everything that it is not in our signal of interest. Interferers or other noise sources have to be filtered, so we concentrate on our band of interest, and then the noise of interest for us, it is the noise that is in this band. So we will typically have to integrate the signal in the band of interest to get the power of the noise. Now, when we talk about noise, we typically handle this as power levels. And this is because mathematically it is much easier to handle noise that is a random process as power levels, but we have to be very careful when we draw conclusions about this, because it happens that noise, it is just another electric signal over our circuits, and then it can actually be represented as vectors that are just moving randomly. And what it is more important, we will see very shortly that when we do noise optimization and we start moving noise sources, they are very correlated. It happens that they have correlation, and then the assumption that the noise can be just added in power quantities only apply in specific situations. So we have to be a little bit careful when with the assumption that noise has to be handled only in power quantities. Now we have the amplifiers have many internal noise sources, as mentioned before. There are resistive components that produce thermal noise, and there are other noise sources as well. Typically, when we have an amplifier, we can connect its output to a spectrum analyzer or to an oscilloscope and start studying the noise properties. So it can be measured at the output. But for practical purpose, it is very difficult to draw conclusions just by looking at the output noise. And the reason for that is that an amplifier can have different amplification, so it can handle the input signal a little bit different. So what we are interested at the end of the day is in the signal to noise ratio, not only on the noise at the output. And it happens that it is much more easier to move all the noise sources from the output of the amplifiers towards the input, so we can extract the input referred noise and do calculations of signal to noise ratio at the input of the amplifier. So when we move all noise sources towards the input, these noise sources, we move it from the output towards the input. Then we can make fair comparisons between amplifier stages. And how do we do this movement of the sources? Well, we will use the two-port ABCD matrix that we have been using until now. It is a little bit easier than using node analysis, but we can also use other circuit techniques. Remember that for your an amplifier or from a device, we model this as a black box with the ABCD parameters completely characterized, all amplifying characteristics. And then we have the following equations for the input voltage equal to AV out plus V out. A, it is related to the voltage gain. B, to the transconductance gain. And then we have the input current equal to CV out plus D out. And C is related to the transimpedance gain, and D to the current gain. So we see that we have that the output voltage, the total output voltage that at the output of this ABCD two-port network is equal to Vn plus V out. So when we refer it to the input, we multiply it by the factor A. What we have it is the following part. We do the same for the current. The output current of this two-port network, it is equal to E out plus E in that we have here. So when we refer it to the input, we can move it as a voltage source at the input using the B parameter. Then we have the following equation, and then we do the same for the input. And then we have something very, very interesting when we start moving the sources to the input. We just group the input voltages and then leave the output voltages to the right. We group at the left the input voltages, and then we have that we can model the input referred voltage source and input referred noise current in the following way, and we can draw here the following conclusion. If we think about this voltage, this noise voltage we had at the output here, when we move it to the input, we have a component here that it is a voltage, and then we have also a component here that is current. Okay, and remember the ABCD parameters, they are just complex numbers at a particular frequency. The voltage, the noise voltage, and the noise current here has some correlation. Immediately we see that they have some correlation. The same thing can be said about the current. We have noise current at the output when we refer to the input, then we have a component that it becomes a voltage source and a component that becomes a current source, and those components are correlated. They come from the same source. So one of the conclusions here is that first, the noise is correlated. As soon as we move the noise from the output to the input, they are correlated. And the second, it is important to keep the signs. We are talking about vectors here, and then it is important to keep the signs. Okay, the noise sources in transistors. We have at the MOS transistor in a strong inversion has the following sources. First, we have this drain, the noise current, and this noise can be modeled with the following equation. It is 4kT. K is the Boltzmann constant. T is the temperature in Kelvin, and we assume normally that T is going to be equal to 300 Kelvin. And typically we call it this room temperature. And this factor gamma, it is approximately 2/3. It is not really a constant. It changes, and but for hand calculations we typically use 2/3. For short channel devices this is a little bit higher. This can go above 1. Okay, this is thermal noise, and then when we basically plot it over frequency, this is this current, it is basically expressed in ampere square divided by hertz. And then when we plot it, it will look like this. It's just an horizontal line, and it is white noise, constant noise at all the frequencies of interest. Then another noise source that we have, it is flicker noise. So it's 1/f noise, and the characteristic of this noise is that it decays with 1/f. So think about this. This is frequency. It decays. Also, when we plot it logarithmic scale, it will do something like this. And it depends on a constant that it is process dependent, but it also depends on the area of the transistors, meaning that smaller transistors will produce much more flicker noise than very large transistors. Now, we can handle the noise with this expression, but something that we typically do is that we use the concept of the corner frequency, and the corner frequency, it is that we find this frequency in which the white noise coming from the drain noise current intercepts the flicker noise, and we call this frequency Fc. And typically we find this by simulation. We can find this one by simulation, and then they allow us to express the 1/f noise, the flicker noise, with the following expression that it is much more easier, as we will see very soon. How to find this point in the simulation, we will see some example. But if we assume that at this point the power of the 1/f noise, it is going to be exactly the same as the flicker noise, then during simulation the point here, it is going to be 3 dBs above the noise floor that it is here, or 1.4142 square root of 2 times if we have it in voltage levels. So it is easy to find the exact position of Fc, this intercept point. Then we have other noise sources. We have that the gate of the transistor, that it is normally built using polysilicon, it is very resistive. So, and then it will generate thermal noise for kT value of the resistance. But with the very good layout techniques, multi-finger, it is possible to reduce this resistance and keep the noise value at acceptable level, so it will not dominate. There is other noise sources, and one that may be very interesting, it is that there is the gate noise, that it is expressed as 2 times the electron charge and the gate current leakage. So there is always some kind of very small current that it is leaking between the gate and the source, and actually the gate and the drain. And this is small leakage current, it is going to produce shot noise. Sometimes important in some applications. Even though it is small, it can be amplified very easily in some amplifier configurations. So most of the time we're going to be worried about these ones, because these ones are the ones that dominate. So you will see for noise optimization we will concentrate on these ones. In weak inversion, what we have is that most of the sources remain very similar, but the noise at the drain current noise changes, and since the channel it is not fully formed, what we have is some leakage current flowing between the drain and the source, and then what we have is that it produces a shot noise. So we can assume for practical purposes that the noise produced in a weak inversion transistor, it is going to be equal to 2Q electron charge multiplied by the drain to source current. And well, that is a kind of big difference with respect to the strong inversion. So we have to handle a little bit different, and we will see the implications. Um, Noise and current sources can be minimized, and this is going to be the topic of noise optimization. We will see very soon. Okay, so as I mentioned before, it is very important to be able to find the input referred noise, because then we can do really comparisons between amplifier and do noise optimization. So we're going to move the noise sources that we have at the output, and we have this 1/f noise, and then we have also the drain noise current at the output. We're going to move it to the input, and we start from the we'll start finding the input referred noise voltage. So to find the noise voltage, what we do, it is just divide the noise current by the transconductance. So we divide by the transconductance, and then we get the noise voltage. That was kind of simple. Then for the noise current, we do the following. We have our transistor here, and then this transistor will have an input capacitance C, and at the output it will have the same noise source that we have already. We have the noise source here, ID DF. Okay, so this is the input referred noise, and then this input referred noise has to give the following noise at the output. It means that this noise, when multiplied by the input capacitance that we have here, will produce a voltage here at the input of the transistor at the gate. This voltage multiplied by the transconductance will be converted into current at the drain, so that has to be equal to ID dF, and then we can find that the input referred noise current, it is equal to ID dF multiplied by G omega C, and this divided by the transconductance. But we have already found that this part of the equation, it is exactly this one here. So we can actually express the input referred noise current as a function of the input referred noise voltage. So we have that at the end of the day, this is going to be equal to Vn times the transconductance at the input of the transistor, 1 over the impedance at the input of the transistor. So we have these two expressions, and we immediately can see there is full correlation. The input referred noise voltage and the input referred noise current come from the same source. They are correlated, and as a complex vector, they are 90 degrees. Have a 90 degrees difference. Totally correlated. So important. Input referred noise, voltage, and current are fully correlated, and as vectors, they are 90 degrees to each other. The capacitance, the input capacitance, for most of the things that we're going to do, we're going to assume that it is coming only from CGS and CGD. And then we talked in previous lectures that CGD, although it is an overlap capacitor, it is actually affected by Miller. So in practical situations, what we will have is that there will be factor that it is multiplied by this capacitance. However, for the calculation that we're going to do now, we're going to assume that this doesn't exist. So we have to remember there might be some important issues of not considering that this capacitance is actually multiplied by the gain. Okay, but for first-hand calculations, it's normally okay to leave it apart. Then we can square these values, and then when we square the noise coming from the drain noise current and the 1/f noise, what we have is the following expressions. Okay, so we have the input referred noise voltage is equal to 4kT gamma divided by Gm, and then this is the noise from this factor comes from the noise from the drain noise current, and this one it is going to come from the 1/f noise, the flicker noise. So it makes very easy to handle both noise sources with the same expression. And then when we go for the weak inversion, we do the same. Then we have exactly the same factor here, and then a slightly different expression. So we have 2Q. This Phi T is the thermal voltage. Ks is the inversion coefficient, and Gm transconductance. Then when we replace the expression for the thermal voltage, what we got is that we have the expression equal to 2kT divided by Ks Gm. Okay, so here we can do a very quick exercise. We talk about gamma is equal to, or approximately equal to 2/3. So when we multiply these two, we will have 4 multiplied by 2 divided by 3 is equal to 8/3. And then Ks, we say that Ks is approximately also equal to 2/3 for hand calculation. So what we have when we divide these two, we will have 2 divided by 2, 3 is equal to we will have 6 divided by 2, and this is going to be equal a factor of 3. So we have here is something under 3. This is going to be below 3, and then we will have here a factor of 3. So yeah, both equations will give very similar result at the end of the day. With slightly similar performance depending on the exact values of these constants. So they are both going to give similar results. Okay. The next part is practical ways to characterize noise. Then we have some setups that we do in our circuit simulator. I have done this for Cadence, but it can be done with other circuit simulators. And what we're going to do, this is one of the alternatives. We're going to use this concept of the self-biased transistor. We put the current that we want in the transistor here, tied to the drain, and then we use a low-pass filter here. This low-pass filter, it is just going to let it pass only the DC value of the drain to source voltage here, only the DC value. This is a correction amplifier, and we add here VDS. So this correction amplifier will introduce negative feedback, guaranteeing that the voltage here it is around 0 volts. And then the output, it is just going to bias the gate at the right voltage. And then we use a very large resistor so that it doesn't affect the AC for AC signals. Very large capacitors here and here for the same purpose. Very large capacitors will not affect the AC signals at reasonable high frequencies. And what I'm doing here, it is I'm just proving this current. I will use this proof to prove the current, and then I will run a noise simulation on this. And the setup for that is here. So we have cadence setup, and you can see it is working here. And when we run the simulation, we extract the input refer noise. So what is a noise setup? So here we have the input refer noise. So what do we do to extract this curve? So let's take a look to the setup. For the setup, we configure the noise simulation. It's very similar to the AC configuration, from starting low frequency, high frequency. Normally you want to do it logarithmic, at least 20 points per decade, and then you select either an output voltage or a current proof. In this case, I proved current at the output. I selected that one, and then the input noise you can also select between a voltage source, current source, or a port. I selected a voltage source, and then I just ran the simulation, and then get different options to plot. If you want to take a look to that, you can go to the main form. You can plot the output noise, you can put the input refer noise figure, and noise factor that normally used in radio electronics, and the transfer function, how the noise goes from the input to the output, and then you can have other possible configurations if you want in voltage divided by the square root of hertz, or as a power level, the magnitude, etc., etc. And then you can add it to the outputs if you want to plot it. So here I have added in the output setup the input refer noise. So it is input refer noise here. Let's talk a little bit about the this curve here, so you can see directly the 1/f noise at low frequencies, and you can see thermal noise a little bit high frequencies, and then you see something funny here, going down very quickly at very high frequencies. At these very high frequencies, this setup doesn't work anymore, and there is basically no gain in this transistor anymore, so those parts are not really interesting for us. Basically the capacitance are shunting the input voltage to ground, so there is no practical purpose for this part anymore. Okay, so how to get the noise corner frequency? We can just let's put a marker here. In this case, we have the thermal noise located at around 6 nanovolts per square root of hertz. Be careful with sometimes cadence misses this amperes and volts. Of course, this is a noise voltage simulation. So what we do is that if this is the thermal noise, we expect that when at the corner frequency, this noise will grow 3 dBs, or square root of 2 times this, and that will be around 8.5 nanovolts. So we check here, we can use the vertical marker here with V, and then we search for around 8.5. So around here around here at 32.2 kilohertz, we found that this will be approximately the noise, the 1/f noise corner for this transistor bias at this particular current level. Similarly to this setup, we have a setup for noise for input refers noise current. But first, let's take a look at some examples here. As mentioned before, for this transistor, 80 micrometer, 1 micrometer length, current 10 microamp. We assume that our inversion coefficient is around 2/3, and then we calculate the transconductance using the equations that we calculated, and then we see that the input refer noise voltage is 7.27 nanovolts. When we simulate in cadence, we get 6, so it is not really far away from what we have simulated. And then, as I mentioned before, we can find this point here rather easily during simulation to get the FC, that in this case was around 32 kilohertz. Okay, so do we go forward, and then we have a similar setup for the input refer noise current. Normally it is not very useful because, as we mentioned before, you can get the information of the input refer noise current rather easily, but yeah, we can also do like this. The difference here is that we have a current source located here, otherwise the setup is exactly the same. Now we have to be very careful because yeah, as we will see very soon in transimpedance amplifiers, feedback resistor connected here will start affecting this setup. So when we run the simulation, we have that as we expect, the noise current grows with the frequency and the capacitance, so we will see this behavior going up here. And then let's take one point, this point here at 1 megahertz. 1 megahertz, the simulation tells us that there will be around 11.4 femtoamps per square root of hertz. Now when we do our calculation again, and then we have the tools to extract gate to source, gate to bulk, and CGD. So in this particular case for these conditions, the capacitance is 0.3 picofarad. We do the calculation at this frequency, 2p 1 megahertz, and then we get that we get 13.6 femtoampere per square root of hertz, which it is not very far away to what the simulator is telling us. It's actually a little bit conservative. Now you might notice here it happens something strange. The equation tells us that it should go like this all the time, but it's not doing it is not doing that. And the reason for that it is that this setup it is pretty much affected by this transistor, this resistor that we put to bias the gate source, which it is going to be introducing some 1/f noise. But that is something that we will take later. Okay.